So welcome to this ENVYO app webinar. I will give a quick overview on what ENVYO is, what we target with it, why we came up with developing an additional, let's say, mapping program to transfer data between different softwares, between different experimental results, to enrich our finite element simulations with LS-DYNA. As you can already see here, ENVYO is part of the DYNAmore ecosystem, which is kind of a group of smaller products which we are distributing to our customers for any application which is related to DYNA, like data processing, data compression, reading out D3HSP plots and such things. And ENVYO is part of the program, part of this program package. Of course, you can also license it as a standalone product. But since I will comment a bit later on during the presentation about how we do our licensing, it's quite important that you have already heard about the DYNAmore ecosystem, because, well, licensing, and that's what we are currently planning to do, will be done within one package, so that there's only one license server necessary to be installed for DYNAmore products. The ENVYO product itself is developed by myself and by my colleague Tolga Usta, who's also within this webinar and who provided useful information and useful slides to this presentation. So this is the standard slide I'm basically showing in every presentation, and those of you who have attended any ENVYO webinar or any presentation from my side about ENVYO, and I guess Tolga is using that slide as well. That's basically the program workflow of ENVYO and what it is doing. So you can refer to as ENVYO as being a mapping program, transferring data from one simulation to another. So the process is usually that we do have a source mesh. It can be a mesh. It can also be a point cloud. So if you have experimental data which holds some kind of information, like a thickness distribution, for example, or temperature being stored on specific points, we would also consider that as a source mesh. And we do have a target mesh, which is usually an LS-DYNA simulation model, which you want to enrich with further information which you have gotten from either a process simulation or from experimental measurement, or basically whatever you can think of. Those data is provided on the source as well as on the target side with different discretizations. There can be different material models to be used, which will have different information stored, like history variables, which you might want to manipulate when you move from one material model to another. If you go from one software to another, there might be history variable information stored, which has to be stored in LS-DYNA at another position. So those are kind of problems we try to target with the program as in a most general way as possible. So the program workflow, as with any mapping software, at least the ones I came across, was that the first thing you have to do, you have to do a geometrical matching so that you are able to perform a proper transformation. Of course, that's nothing which the user is doing, but we do have specific features within ENVYO which allow you to match the geometries. Then we work basically on point clouds. So we try to consider where the information has been stored. If you have an LS-DYNA input mesh, you usually have temperatures stored on nodes, thicknesses as well. You do have orientation on elements or on integration points, depending with which kind of modeling approach you, for example, consider your metal forming with specific rolling directions, or if you have a composite material with laminate stacking sequences, then you have orientation information on the integration points at different positions, or even just on the element center. We generate those point clouds to perform the data transfer. That data transfer can be done in several ways. The most simplest one is a standard closest point approach. But we do have more sophisticated approaches like point projection and performing of finite element, averaging, and interpolation techniques. So there are different options available here. Then depending on what you want to do, the program is performing a homogenization, usually based on what you provide and what material model you are targeting, or what your kind of target application is you're looking at. And we perform a homogenization. Then we do handling of the history variables. So as a user, you have the possibility to, for example, to perform mathematical operations with the history variables. There are some predefined variables like the characteristic element length, or let's say temperature, whatever you can think of, which you want to use to play around with the values you have transferred. And then finally, we create a DYNA in file, which is the standard include file we refer to, which is used to initialize your LS-DYNA analysis with a subsequent with initial data. And well, that's one of the restrictions maybe compared to our competitors. So our main targeting software currently is LS-DYNA. We might be extending features to some ANSYS products, or that could be something we could be aiming for. Furthermore, we currently support the VMAP format, which is the approach which came out of a European research project to generate standardized simulation result data storage, so that it will be easier for both customers as well as for people developing software tools, such as a mapping program, to handle the result data from different solvers. Because actually once the interpolation techniques are established in such a program, most of the time is being used actually for reading and writing respective result file formats and input formats. Working with the standardized format would be highly beneficial here. The agenda for today, as I've already introduced ENVYO, more or less, I will mention most of the general functionalities already, but I do have a few more comments on them. And then I will, so that's basically for those who haven't heard of the program yet. Then I will follow with some general improvements on what we've been working on in the recent past, like some things which basically apply to every of the features. Then I will have an overview on applications where we have customers who've been using ENVYO for different things they thought are interesting. From the nature of how the program has been grown, there is a heavily used user community for short fiber reinforced plastics, but we've been rolling out the program and continuous fiber reinforced modeling as well. We do have some rather new features related to image processing. I will comment on that with a couple of slides, and then we do have some applications in metal forming, but also on stochastics and micromechanics model initialization. So I will have a few more slides on that as well. Then I will have some comments on licensing, since for those who are using the software already, we have, as I said, we do have a change in our license server system, and that will be rolled out with the next release. And there are some further things I'm thinking about developing within the upcoming month or years, which are on my list. Nevertheless, I always see software development as something which is not like a closed solution, so to speak. So the program is highly dependent on user input, and on a daily working basis, I learned basically every customer has its own process chain or its own ideas of what result data he wants to link to his simulation to increase his accuracy. So we are open to input and implement new features based on customers' requests. So to the general functionalities, as I said earlier, we usually start with geometry matching. We do have some, let's say, semi-automatic algorithms which we used. One of them is the 4-point congruent sets algorithm. The other one is the iterative closest point algorithm, which is kind of a standard approach. I say semi-automatic because the iterative closest point, we usually work based on nodes. So the user can define a subset of nodes which he wants to match on source and target side, and then it's like a minimization problem which is being solved to get the geometries matched before the data transfer is being applied. In addition to that, we do have some manual mesh operations. Of course, I mean, if you know your transformation matrix, or if you know that your vehicle coordinate system is different to the coordinate system you've been using in your forming part, it's usually pretty straightforward that the users know the transformation matrix, and then you can basically just provide the transformation matrix so that the program performs the transformation prior doing the mapping. If you come from different simulation disciplines, for example, short fiber reinforced modeling, or you move onto a crush model for a short time impact situation, there's usually need to change the unit system. So we do have some predefined unit systems implemented, which allow you to convert the unit system from one system type to another. And that usually includes the scaling of the model, sometimes changing the values of the stress, the magnitude of the stress values. And of course, if we do transformation like rotations and things, we consider that as well for fiber orientation tensors, for example, or directions which are provided in global coordinate system. To speed up the mapping algorithm, we use a bucket sorting algorithm. So we cluster. This is a rough representation, but it shall give you an idea of what it's doing. So it's basically generating these areas we call buckets, and we perform the search within these buckets or within extended radius to create our search areas for elements, and therefore we do have a significant speed up in the transfer than if we would search through the whole range of points which we have. As I said already, the mapping is based on the data storage location. So we do data transfer depending on if the data is stored on elements, nodes, or integration points. When talking molding analysis, sometimes the information is stored on the element center, sometimes it's stored on the nodes. So that would also be an application for where we need to consider where we do have these information data provided. And then the data transfer is based on different methods. So the standard approach is the closest nearest neighbor one. So you just look for the nearest point and you transfer the data. Of course, we've added more sophisticated interpolation techniques. The most natural one when coming from finite element simulations, you usually project points from the source into the target or the other way around, and try to perform, or you try to identify the natural coordinates in the respective element system, and then you perform an interpolation based on the data you have. There are other algorithms available, like a distant weighted average based on Shepard's method. And we are investigating on tensor interpolation based on the tensor invariance that works currently just for positive definite tensor data. So it's an application within the range of, if you model short fiber reinforced plastics, for example, these tensor data you get from molding analysis, those are usually positive definite. And then one could apply these tensor interpolation based on invariance. So that's still some ongoing research. I usually say that, well, consider some of the data you already have within your analysis is usually better than not considering data at all, especially when it comes to direction-dependent material properties. But of course, if you want to look a bit in more detail, you are sooner or later will end up using more sophisticated interpolation techniques as well. A few more comments on the general functionalities. So we do have a graphical user interface, which helps for the mapping file generation. It's nothing which is like really sophisticated, but it's basically you see the input here on the right. That's like the main startup window. Then you can either open a file or you can start to create a new project. And what it should usually help is it should help the users to select where he wants the data, where the data is coming from, and where the data is supposed to go. So we currently have the mapping clustered based on discretization. So if you do have a shell source and you want to go to a target shell, then basically that the mapping main command is shell to shell mapping. If you go from solid to shell, it's solid to shell. If it's beam to solid, for example, you can say, well, beam to solid is the mapping algorithm I want to use. And depending on which of these algorithms you choose, you do have different options like general mapping options, material options for fiber mapping, or representative volume options, and further options for history-variable handling. You can use the equation parser, or you can activate clustering methods, which are sometimes needed, for example, in the area of grayscale mapping, where I will talk about in just a few minutes. We are working on, currently it's still within progress towards steps in evaluation of the mapping data. That's kind of a hard topic because you always have to think about what is the reference actually. So if you start to transfer data and if you start to average the data, you already use some information, lose some information. So if you want to compare it to like your original input, then it's hard to decide what would be a proper measure to evaluate the quality of the result mapping. But that's something we're looking at, and if customers see a need there, and if there is a request on, or if you have an idea of what would be a good measure to compare these data, that's what we are open for. The main target is that we still have maximum user control, so the user can basically do things the way he wants them to. Nevertheless, we start for specific applications to add like predefined functionalities. So, for example, mode flow to shell mapping is like a application dedicated mapping option, which allows you to transfer mode flow to structure analysis, or mode X data to structure analysis. So those are kind of already dedicated features, and usually, or probably at some point, there will be people who will always map result data from map 24 to map 36, and then we can of course add like a set of pre-established routines which are dedicated to these two material models. But until then, we wait for customers' feedback and would of course simplify the approach if that is needed. As you can see here, we provide release notes. So we do have a manual, which quite often has a few hundred pages already. We usually come up with release notes, which summarize the features of the current release. We just finished the debugging of our 2023 release, and we're about to distribute it to our customers also together with the new licensing system within the next couple of weeks. So now you have an idea of what ENVYO is doing, at least roughly, and what the general functionalities are. Enhancements we've been doing in the past, and I think all the developments for the GUI, they go back on Tolga. So he's been working on the enhancement of the GUI, and he created a new look. So we have like these green colors and yellow colors, which kind of highlight the options you've been selected into the specific spaces. What you can also do, you can open an existing mapping.in file. I've mentioned the mapping.in file already, just to give you an idea of what it is. That's basically our input file. Like if you use DYNA, we have these key file formats, which are ASCII-based input decks, and you use those to start your simulation. We do the same thing in ENVYO. So we create an ASCII input deck, which holds information of what data should be transferred and what the file names are. And that's what we call mapping.in file, and then use to run the program. We kind of stayed away from creating our own additional preprocessor, because there are so many preprocessors around, especially when working in the DYNA environment. You're familiar with LS Prepost, which is for free. So there is the possibility to kind of call LS pre-post directly from ENVYO, same as access through the manual. And of course, you can also start ENVYO directly using that kind of startup button here, which will run ENVYO directly from the input file. But at least to my experience, but I mean, I always have like a dedicated developer view onto things. I usually, once I have created a mapping in file for a dedicated use case, which you usually use every once in a while, and it's kind of repetitive procedure, you just change the number of integration points or the name of the file name, and then you should usually be good to go. We've had some functionalities for multiple transformations. So sometimes there's a case where, well, it's a generic example, but sometimes where there's the case where specific areas do not fit to each other, like in this case. So the user wants to perform dedicated transformations to get these sawtooth areas into the same position as in the source map to perform a proper data transformation. And therefore, we have the capability to perform multiple transformations, and that capability has been rolled out to basically all the mapping options which we have now. We've also been working on element and nodal thickness averaging options, which you can imagine if you have like a ripped part and you do a mapping from one node to another, there might be some non-linearities, or you might not get a proper transfer depending how the data is being handled. And if you perform an averaging, you will lose some information here at this point. So now we've created an option which allows users to properly consider these ripped part in the thickness distribution, and therefore also in the generation of the point clouds for the elements. We also consider the shell reference plane and lock, especially that's important when we use with offsets for patched fiber reinforced plastics, for example. Some further applications of that were the general was the general introduction, and then we have some further applications or a few of applications for which you can use ENVYO for. So ENVYO can be used for short, long, and continuous fiber reinforced composites. We target specific material models, especially for short fibers. There's a dedicated list of material models which we currently support. You can support the direct initialization of the orientation. So if you do have a molding analysis and you want to run your model later on with a MAT58, which is none of these like specific material models for short fibers, we do provide the possibility that you create elemental composites through the data transfer and then use these with any other, let's say, random orthotropic material model. We also support clustering methods. So we do have people who generate several material cards for dedicated fiber orientation tensors or fiber volume fractions. And then when you do the transfer, you just kind of perform an average of the information which is being transferred, and you assign one of these specific material cards out of like a database to that specific integration point using elemental composite. We've been working a lot into these image processing themes in the past. We actually started with the wood forming application, where we have the question of different material properties of early wood and late wood, depending on the growth of the tree. The use case I will show is for vehicle interior design components. Then we had a research project on adhesive modeling, where we tried to consider the viscous fingery effects, which one observes usually during the KTL process. One use case has been packaging materials, where the packaging didn't work as it was supposed to be. So there has been an X-ray scan of the packaging material generating shell surfaces. And from the offset of these shell surfaces, we could initialize thicknesses on the elements to improve the accuracy of that packaging simulation process. And one of the newer things we do is we test material calibration capabilities based on GOM RMS measurements. So we try to get information data from that into our model setup to improve material calibration. And I see a huge capability here, since even more measurements and everything, everybody's basically measuring everything in every state, and why not use those as input parameters as well for your simulation? So I see that's a good application. Metal forming applications, or metal processing applications have been used. For metal forming, you can use ENVYO to consider bake hardening effects if you are looking at the KTL process of a vehicle, for example. Then you can, there's the JMAC equation implemented for a specific case, which gives you the current hardening degree at the integration point. You see, ENVYO cannot just be used for fibers, it's available for any other application as well. And since my colleagues here in the office next to me is working on IGA, isogeometric analysis, we've also started to map data from forming simulation to IGA crushing analysis to see if there is a way to consider old finite element data in new IGA applications. Of course, you can also use ENVYO for axisymmetric problems. So if you do have a 2D model and you rotate it about 360 degrees, you can transfer the result data like initial stresses or plastic strains onto that new model. There are some particle methods which we support. So, I mean, of course, in DYNA, you can basically do a full coupled particle and structural analysis. Well, nevertheless, sometimes people just do a particle or a fluid simulation without a direct coupling to the structural, but they can create a pressure output for these particles or for these elements, and then they want to follow up with a structural analysis. So we have some capabilities to transfer the resulting pressures as load segments into DYNA meshes. I will have a few more slides on stochastic parameter initialization, and I've been working to couple to manufacturing data as well, especially in the case of 3D printing, but that is currently not our main focus. Just as a quick summary on what we support for short fiber reinforced plastics, we've had a few developments going on with also a couple of years ago, we've been investigating the usage of MAT 157 for short fiber reinforced plastics. We've been looking at this lower bumper stiffener component. We basically in MAT 157, you can initialize material directions, anisotropic elastic stiffness, anisotropic plasticity, the hardening curve, and also failure parameters on each of the integration points, and therefore you need a dedicated mapping tool. For MAT 157, compared to other material models you have to perform this homogenization in advance, and therefore ENVYO supports rather simple homogenization values like Tandon-Weng and Harpon-Tsai, but we also support the standard Mori-Tanaka mean field theory to derive the elastic stiffness components. Nevertheless, you will sooner or later need a kind of meta model-based estimation of plasticity and the anisotropic plasticity parameters based on your orientation tensor shape. And that's what you could do, for example, together with LS-Opt, defining a set of input parameters, create a meta model like a feed-forward neural network, for example, and then through a mapping process, identify the unknown orientation tensors and let LS-Opt calibrate you the resulting or the missing components of your hardening curve and your anisotropic plasticity. Since this is just a wrap up, I will not go too into detail of what you can do there. We've added another orientation averaging technique. So the default was Advani and Tucker. We've added the orientation averaging based on Dre. And until a couple of months, we just supported linear, quadratic, and hybrid closure approximations. And I've added the orthotropic fitted and the orthotropic smooth closure approximation which is needed as an input to calibrate the elastic stiffness matrix. As I said earlier, we've also been enhancing MAT 157 towards the assignment of specific material cards. So if you have a, let's say, database of material cards with specific properties, that can be MAT anisotropic elastic plastic, but it can also be any other kind of material, basically, which provides through the MAT anisotropic elastic _ title keyword some ENVYO orientation information. Then ENVYO will actually, if you use that clustering technique with short fibers, ENVYO will look up based on the input, will search for these dedicated orientation tensor files and assign these material cards to the respective integration point, so that you would not initialize all the properties through the initial stress card, but rather have a dedicated set of material cards on each integration point. And it also works quite reasonable from a mapping perspective, but also from a, let's say, result point of view. So if there's a good set of calibrated material cards, your finite element analysis might actually be even faster using that approach, because there are not as many lookups on the values on the integration point as if you would have a reduced amount of material data. As I said, we support different closure approximation methods, and here we have basically a list of solvers which we tried to link to ENVYO. So we support Moldex 3D, Moldflow, and 3D Timon. I think we also support CAD mode through the VMAP file, and here we just don't support just the mapping to shells. We support also the mapping to solids. So hexahedral, pentahedral, tetrahedral elements can also be handled for this material model, but also for the other material models. So as I said, most of this work has been recently done for MAT 157, but we also support this MAT 215, the initialization of that. It's a bit of a different approach, because all the homogenization which is done for MAT 215 is done within LS-DYNA, so you don't need ENVYO in that case to perform the homogenization for you. You just need ENVYO or any other dedicated mapping tool to transfer the orientation tensor and the eigenvalues of the orientation tensor. So the directions and the eigenvalues, and then the homogenization itself is being done within LS-DYNA itself. And the same accounts for material 303, which is a new material model which has been implemented and is available in LS-DYNA from release R14, so from the current release onwards. It's a machine learning-based approach based on a deep material network. That's how the developers call it. And the material model itself has been trained using representative volume elements. And you will need a program. LS Prepost can do it as well, but we can also do the ENVYO, which transfers the orientation tensor from any of the below listed molding simulation software result data towards your structural model. With respect to continuous fibers modeling, we have been collaborating with a customer who wanted to transfer data from Abaqus Compro to mesoscopic constrained shell and solid models. So we supported him. Basically, the Abaqus model held information about solids and respective orientations of the solids, and we supported the customer generating shell elements out of these orientations, which can have a respective row ring with a dedicated element length. And then he could also select how many elements he wanted to have across the width of the roving, and then we're able to generate these fiber tapes to create these tubes. And one of the use cases could, for example, be a hydrogen pressure tube, for example. And in this case, ENVYO is used to transfer the Abaqus Compro model and to generate these, including shells, which can then be used together with the constrained shell and solid keyword card, for example, to perform mesoscopic modeling. Within the ARENA 2036 research environment, we've been investigating on linking several process change next to each other. So one of them, and with that, there came different enhancements to the mapping software itself. So we had kind of an optimization result from Altair software, which provided us patches where we would need to have a reinforcement in our final structure, which in this case is the hood of an electronic casing within a vehicle. And we could derive some specific elements which had dedicated orientations, which are or can be considered as reinforcing patches on our resulting structure. And well, we were able to map those onto the mesh we want to use for the forming. So that's basically what you see here. So this optimization has been done on the final structural part. So what we had to do is we had to kind of get this information onto the kind of final structural mesh, and then through the usage of the deformation gradient, we could calculate the reinforcing patches and the respective orientation of these patches onto the blank sheet prior to the forming process. And we also overlapped that with the results of a weaving simulations. These weaving simulations have been performed with beam elements, and they had the inclusion of a sensor band, which is during the manufacturing process used to consider to measure effects of temperature or accelerations and such, and should be used to, well, first evaluate the manufacturing process of the part, as well as the life cycle of the part. So what's happening once the car is being once the component is being established or implemented into a car. And of course, we also want to use this measurement result data within ENVYO to consider or to evaluate the molding process, and also to see if some design changes, for example, like temperatures or some accelerations which have been unwanted, if those can be represented either in the simulation or if they can be used as simulation input to predict if the component is still valid. So these basically two disciplines have been brought together, and then we can perform a draping analysis. We've added the option to create element shell offset composites with a flat lower option, which basically ensures that the reference shell we use is the bottom surface of the shell. That's what we need to do because otherwise we would have a non-symmetric distribution. But from a manufacturing point of view, you of course add these patches on top of each of the layers, so you can consider that properly. And we also see that in certain areas, for example, if through the searching process we can't identify a ply or a specific layer is not available, it creates this -1 value for post-processing and pre-pros when the analysis. So we have the same number of integration points through all of our parts. But at some point there's just no material available, so therefore we support how LS-DYNA is basically considering that. And we can also introduce the influence of the sensor band, for example, also with the clustering method, where then a dedicated material ID is assigned to that integration point, where the sensor band, for example, is being found. Well, with respect to that, we've been using matte reinforced thermoplastic to perform the draping analysis, and there has been enhancement made by Thomas Kloppel. He added a crash option to MAT 249, so it's now MAT 249 crash, and we've enhanced the mapping process so that we can also initialize directions for the history variables for this new crash model, which would allow the user to stay within, let's say, one material family when he's performing the simulation chain from component design through a draping process, and then a final structural simulation. We've also been working on kind of an enhancement of the fiber averaging scheme. So you can imagine if you do a draping analysis with several layers, which have individual numbers of fibers through the thickness, individual numbers of integration points. By the end of the day, you just want to use one shell discretization, for example, with different integration points through the thickness. Then, well, we need to know how you want to average these data. And we came up with a bitwise entry definition, which would tell us which fiber information from which layer, from which integration point. So with layer, we refer to the different layers of shells. With integration points, we refer to the respective integration point position through the thickness in the shells. And with fibers, then we look at the we refer to the respective fibers within that integration point. And that's how we basically do the averaging with this new method, which seems to be a bit more readable compared to the other ones. Then I come to the field of image processing, and that's work I've been done together with a PhD student at Mercedes, who wanted to consider, as I said, the influence of early and late wood zones within his simulation model. We've had 2 publications about that topic. What we basically did, we implemented it's a simple clustering method, which is based on grayscale values. So we used GIMP image manipulation software to transfer the pictures, which have been taken prior to the forming process of the component. And then we've created an option to define several clusters, which get assigned a specific part ID if the grayscale value is within a specific range. There's no need to just do that for 2 parts. You can do that for 3 or for 4 or for how many you want. And well, the general idea is what you see here, that if you then assign to these different parts, if you assign different material properties, you are more predictable in the simulation of these components during the manufacturing, but also kind of during a stamping process when you try to predict failure with these different material models within your model. Then I said what we've been using this method for adhesives as well. So for the wood forming, we had the capability to do that with shells. Now we also map to solid and cohesive elements, so we can initialize for a specific material model in LS-DYNA. We can initialize a damage factor, which is based on the effect of the viscous fingering. So what ENVYO is doing, and what we've basically demonstrated here in this example, it's identifying the gray values at a certain area, and depending on if we are more white or if we are more black, we assign a specific damage parameter to that specific element, which is basically describing the coverage of the adhesive in this specific area. And as you can see here in this example, where we have the force over displacement of KS2 specimen, we tested that for several element sizes, and we see it doesn't seem to be sensitive to the element size. But of course, it's sensitive to how you prepare your image. So we are working on enhancing or trying to automate this image processing step, which you usually need before you perform the mapping. So I did a quite well calibration, or quite well a cleaning of the image for the image 2 to 4. The first one, you see that it has some kind of speckles there, so there seems to be a high coverage of adhesive for the simulation, and therefore we reach higher forces in that case. And to do that, we have worked on adding the OpenCV library as an additional feature to the code. It's not in an official release currently because it's still under investigation. And the idea was to help customers to kind of automate that process of detection of the the boundaries of the viscous fingering area. And we've also added this feature, or we are trying to use that feature within another research project, which is called HiCope, and now we're back at continuous fibers. We do have some micro CT scans of these filament woven structures. In this case, we have like 4 layers with different orientations of a wound cylinder. And we've applied the mapping program by identifying different grayscale ranges, which refer to well-dedicated directions. You can, the finer the meshes, of course, the more accurate you are. If we look, for example, in this area, we can at least see at a small degree that there seems to be a shift in orientation. We do have some matrix-rich zones in this upper area, so that's what's being represented up here. We also see the weaves of the rovings, actually, and we can detect pores. And again, the idea behind that is that we do have dedicated material cards for pores and fiber orientations. So each grayscale value gets a specific material card. And with that, we could at least create a validation use case based on a numerical experiment to see if such an approach going from micro to, let's say, a mesoscopic modeling approach, if that would help us to predict on a representative volume area, so to speak, to predict the response of such a material model. A subsequent step would be orientation initialization. Of course, if these are like really like high microscopic pictures, so you can really kind of zoom in and try to identify the orientation through the shape of the shape you get of the ellipsoid if you cut the fibers, but then you have to like really go into detail and identify the local orientation. You could do that for each of the fibers, of course, but that's probably a bit beyond of what we are currently able to do. But it's something we want to keep in mind for future developments. As I said, we've been working on GOM material identification and initialization. So here you basically see the transfer of displacements of a GOM measurement onto different element sized or different element length models. And we've basically ran these models as a displacement driven simulation with all the nodes having a dedicated displacement. And basically what you see here is we get all these different curves which show more or less the same force over time answer in that case. And yeah, of course, the finer the mesh, the clearer you get the same plastic strain as in the measurement. But well, the force response seems to be more or less the same, and we hope that we can enhance material calibration based on that. And we've also been working on other methods which try to identify crack paths, and then through iterative steps and deformation of only the crack path elements, help the user to identify a plasticity curve based on different element lengths. So if these data are being mapped, then you can do the same thing for different element lengths as well. For metal forming, as I said, we can transfer, or we added the capability to transfer initial temperatures. We can do thickness mapping from solid elements to shells, as you see in this example. We can generate solid elements based on a shell mesh. We also consider if adaptivity has been used by creating the restrictive constraint cards, and yeah, we don't have any hanging nodes here. We initialize the temperature on the bottom, the mid, and the top surface of a shell element if it's coming from a solid temperature simulation, for example. And as I said earlier, we also support the thickness mapping from shells. So if you have a top shell and a bottom shell, and you have a mid-surface mesh, so to speak, and you want to get the thickness generated through the offset of these two shells, we can also transfer this information as a thickness input, for example, for a packaging use case. We've recently added the capability to map to IGA elements. So we consider isometric analysis, and we map the thickness to initial strain IGA shell, and we map the stresses and history variables to initial stress IGA shell. So the approach is a bit different than to standard finite elements, but it's it's under investigation, so to speak. And of course, also the mapping result depends on how coarse your IGA discretization finally is. But that's basically the case for all the simulations we've done. So if you go from a very fine to a coarse mesh, you at some degree lose information, and you have to kind of think about if the approach is adequate enough or not. Last but not least, we've been working on stochastic initialization. So you can provide to ENVYO, you can provide a mesh, and you can provide a stochastic distribution using MAT 157, and it will either reduce the material properties or it will create pores into specific representative volume elements. And here you see some examples of a paper which we've published together with the DLR, which holds these pores, and also an evaluation of stress versus strain for RVEs with different influences through the inclusions. We've been working on transferring solid data to cell elements, to beam result data, so the directions of the beam, to solid meshes, so that you can have element solid ortho, for example, for such a representative volume element, and then perform analysis with that. Before I conclude, this is a remark for those actually using ENVYO already. So we are working on the to kind of standardize the distribution of all the DYNAmore smaller software tools within the DYNAmore ecosystem, and therefore we've been working on a new license client. So you have the software basically, which goes to the ENVYO client, checking the license request, and then you can have either a single server or you can have a server triad. If you use ENVYO, there's no need for the license client, because there's a direct contact from ENVYO to one of the clustering machines. But otherwise, if you use one of the other tools, it's going through a client because they are written in different programming languages. That helps us to get a bit more flexible inversion distribution. The licensing models we have will remain the same. So we have node-locked server and server triad licenses as we've had before within ENVYO. And it comes with the establishment of a DYNAmore ecosystem network license, which is used. But if you are a user of the program, this is usually nothing you have to bother about too much, because it's usually discussions between us and your IT to get the server running, and then you can use the software. Further developments I'm looking into, I'm showing like this thing since a couple of years. There has been this constrained beam in solid forming simulation for SMC materials, and what I always wanted to do was perform a mapping through an orientation averaging onto a DYNAmesh for a structural simulation. Maybe this year or next year I finally find the time to do it and to evaluate with one of the material models which we have in LS-DYNA for such specific models. Another feature which I think is quite interesting is we are currently developing a new human body model, which is called HANS. So there's also an information day coming up about that. And I got the request to map measurements from the ribs of the bones onto, for that specific human, to measure to transfer the thickness of the bones to this model, so that it will have an increased accuracy as well. So there are many ideas to use mapping and data transfer And that's what we will help you or try to help you with our mapping tool ENVYO. So as a summary, we usually plan to have 2 official releases. That sometimes works more or less. The tool itself is available for Windows and Linux, both the user interface as well as the standard application. You will usually get an executable, which is named ENVYO V, and then, well, the next one will be 2023 1 something. We provide official release notes within the manual, but of course, we also provide such webinars, which give the users an update of what the program is doing. These webinars are also provided on our YouTube channel. We are working on an automated version deploy, so well, that's what we do. You get a package which holds all the libraries you need, and then you should be good to go. As I said, we integrate ENVYO in the DYNAmore ecosystem. Of course, you can license it as a standalone, but you will have the same license, however, for all the DYNAmore tools as well as for ENVYO. So that should ease the process a bit. Before we distribute the code, we usually do a QA. So we have 180 plus customer and development examples into our optimized QA, which we then let the version test for and perform debugging before we hand the software out to you people. Yeah, and finally, we are working on the support of the VMAP standard. We're also part of the VMAP standard community. So the more or less we can link to this standard, the more software tools we provide automatically if they are supporting the standard as well. And with that, I'm at the end of my presentation. It's good to see someone just joined, so we have a few more people have been interested in this presentation. I will stop the recording now. It will be later for further rehearsal. So if you want to listen to it again, or if you have questions which haven't been answered, you can re-listen to that. Otherwise, I will stop the recording now. You can raise questions if you like, either directly after this course. I think I can enable the microphones for you if there are questions. Otherwise, of course, you do have our contacts and can reach out to us anytime you like. Thank you.